All right. For using significant figures, we're going to skip this part right now and go down to the rules, because you know we do have certain rules that you apply when you're just looking at a number now and trying to decide how many significant figures the actual measuring device had. So back up here, we were looking at our measuring device and we were making certain that our value was read to the correct number of significant figures. Now what we're going to do is try to find out that if you look at a number, how can you tell how many significant figures the actual measuring device was just based on the value that you're given. So we have rules for sig figs, and you'll recall some of these. Non-zero numbers, if you're looking at a set of a measurement, are always significant. So non-zero numbers are always significant. All right, non-zero. So if I have a number like 1427, got to give it a unit, we'll say meters. All of these are non-zero numbers. There would be 4 sig figs represented by the measuring device. All right, then we get into our zeros, and they're the problem causers here. Leading zeros are never significant. Leading zeros never significant. And by leading zeros, we mean if you have zeros in the front, so 0.127, there's a, got to put a unit with it, we'll call it grams this time. This has 3 sig figs. A leading zero is never significant. 0.0012, stuck on 127. Oh, let's throw in a 3 there. Meters, there's 2 leading zeros, they are not significant. This one again has 3 sig figs. And then we have captive zeros are always significant. And by captive, I mean the ones that are sandwiched in between non-zero numbers. So for example, if I had 5, doesn't want to work, 580.01, we'll use grams. These are captive zeros. They are in between non-zero numbers. They are always counted as being significant. So we have 1, 2, 3, 4, 5 sig figs represented by the measuring device for this particular measurement. So we have situations where zeros are never significant. We have situations where zeros are always significant. And yes, we have situations where zeros are sometimes significant. And they are trailing zeros. And do you remember the situation when they are significant? Yes, when there is a decimal point. So we have a situation with, let's say, 55,000 meters. These are trailing zeros. There's no decimal point indicated, so there's only 2 sig figs represented by the measuring device. But throw in a decimal point with the meters. That's telling your reader of the data that you took the time and the effort to measure to the 1 meter place, that your measuring device was that good. So 1, 2, 3, 4, 5, you actually have 5 sig figs represented by your measuring device. Now the mathematician might look at these two numbers as being exactly the same. The scientist doesn't. This one, we know they only had a measuring device that would go to the thousands place, but for this one, we actually had a measuring device that went to the meters, or measured to the nearest meter. So we view them as very different. 3 more significant figures here than there is up here. The last rule, exact numbers are infinitely significant. Spell that right. And missing an E. See, I need you here to help me with my spelling also. Exact numbers. When I'm counting, I have 3 students. There's no question as to parts of students. 1, 2, 3, or a dozen apples. Whenever you are counting something, you have an exact situation, so you have an infinite number of significant figures. Whenever you're dealing with a conversion, and by the way, this is one that I'll have you memorize. 1 inch is equal to how many centimeters? Do you remember? Right, 2.54 centimeters. Whenever you're working a conversion, it is an exact number, an exact conversion here, so they're considered to have an infinite number of significant figures. Then when you have a constant, for example, 2 pi r. Anybody know what that is? Yeah, that's the formula for finding the circumference of a circle. Right. This is a constant value there. If you say 2x or 2 pi r, when you're using a constant, then that also is an exact number, considered to be an exact number, so you have an infinite number of sig figs. All right? So there's the basis of your sig figs. Now, when you're dealing with mathematical operations, the rule for mathematical operations is your number cannot get more precise just because you performed a mathematical operation on it. So we have rules that have been developed to account for the fact that we have to add, subtract, multiply, and divide numbers all the time in science. But again, a measurement can't get more precise just because you've performed a mathematical operation on it. So for example, if I take 0.2 centimeters and measure a square or a rectangle, and it's 0.2 centimeters by 0.8 centimeters. All right, if you multiply these two numbers together, you get 0.16 centimeters squared. Now here I only have one sig fig, and here I have 1 sig fig. In my answer, it's represented now as 2 sig figs. So it looks like I've actually gotten more precise just because I multiplied the two numbers together. We don't have that happen in science. We would round this so that there is only 1 sig fig in the answer. We would round this to 0.2 square centimeters. All right, so you cannot get more precise just because you've added or performed an operation on the two numbers.